All right. Good evening, Sai and Tanisha. I guess soon I think more people will join. So what we will do is we'll start now. Let them
Good
join.
evening, sir.
Good evening. So um, so today what we are going to do is we'll solve this one problem. And this problem, you know, includes solid propellant rockets. So if you look at it, last we have done enough discussion about the combustion chamber temperatures and characteristic velocity, how to find all those in the last class. So I hope that would be useful for you to submit the week 7 assignment. So uh, today what I'm going to do is it is going to be related to your week 8 assignment. This is to find how to find the chamber pressure in the rocket motor. So we found the temperature of the rocket motor based on the energy balance. Now we also need to find the pressure on the rocket motor, that because that is going to decide what is going to be your C star, your thrust of the rocket. Everything is going to depend on the pressure and temperature inside the rocket. So this week we are going to deal with only solid propellant rockets. In the upcoming week we'll deal with the liquid propellant rockets. Okay. So let's get started. So if anyone have any quick questions, if you want to ask, you can ask now. If it is a lengthy clarification, we can have it at the end of the session.
Sir, I just had one question.
Yes, Sai, please go ahead.
Sir, what exactly is divergence angle and half divergence angle?
Okay, so divergence angle and half divergence angle is related to a conical nozzle. Okay, so in a conical nozzle, so you will have a convergent part and then you will have a divergent part. Okay, and now let's say if you this one is actually the divergence angle, you can say beta. It's actually semi divergence angle because you are considering only upper half. So let's say if you completely draw a nozzle, then this total angle will be your, this 2 beta will be your divergence angle. Okay, is that clear?
Yeah, I got it.
Okay.
Yes. Sir, what is like half divergence angle? Like we take cos square of beta by 2 for the fractional loss.
So half divergence angle is this part beta. This beta is
Okay.
half divergence angle I am telling. So if you consider this as a beta, then this will be beta by 2. That's it.
Okay.
Okay. Okay. So if there are no more questions, let me quickly go ahead and solve this problem. It's a pretty easy. Okay, sure, sir. Okay. So I have only one question today. So the question is about the solid propellant grain combustion. So what do we have here is a radial burning solid propellant rocket. So basically it's a radial burning rocket. Has a hollow cylindrical grain. So basically it's a the propellant is like a cylindrical grain and it is radially burning. So the inner diameter of the grain is given, outer diameter is given, length of the grain is also given, the throat diameter throat diameter of the nozzle is given, and also the burning rate of the propellant is also given. So this burning rate is actually coming from experiments. Okay, we cannot find this burning rate, it is coming from the experiments. You can even model it using advanced CFD based model, but people haven't been successful using using modeling techniques. But basically this is the characteristics of a burning behavior of a propellant. It is coming from the experiments. Okay, and then it is going to depend on pressure. So what we are asked to find is, let's say if this is the propellant, if this is the grain, propellant grain, what would be your initial and final burning surfaces? Okay, what would be the pressure, what would be the burning rate at initial and final, what would be the total duration of burning, okay, and what would be the mass flow rate, because the mass flow rate, it will either increase or decrease depending upon the grain configuration, and that is also going to affect your thrust profile, and also initial and final thrust as expected. Okay, you can assume the density of the propellant is also given, the values of C star and CF is also given. Okay, the rate, these comes from the uh, C star and CF is coming from the analysis, right? We already did how to get that. So this week is purely about how to get this pressure, mass flow rate, which would be useful for you to calculate the thrust. Okay, so let me quickly draw a schematic of it. I hope everyone understood the problem. Maybe if I draw the schematic, you would better understand it. So since it's a solid propellant rocket, let me draw something like this. So this is how solid propellant rocket looks, and what they said is it's a hollow cylindrical grain. So the propellant will be something like this. I'm just drawing a cut section. So they make this propellant, they cast it, and then they put it inside the rocket motor. Okay, and we have a nozzle here. So this is the nozzle, and this is the combustion chamber. So from here what happens, let me also draw like a center line. Okay, let's say you take this as a radial direction, so it's going to the burning is going to happen on this surface, and this surface is keep on going to get this surface is keep on is going to get regressed. So let's say if I want to draw a side view of it, I can draw, let's see how accurate I can be. Let me be consistent with the colors. And then you have, this is the cylindrical grain we are talking about. Okay, and what is given is, they are given this initial diameter, the inner diameter, and they also given the outer diameter of the grain. So this is like d0, and this is di, and they have also given the length of the grain. So all these are going to affect the rocket thrust and also the pressure. Okay, what else is given? Outer grain, inner grain, length of the grain, and then nozzle also is given, nozzle throat diameter. Alright, and then burning rate is given. So let me quickly write down all these values. So while I write down this value, can you guys think how to get initial and final burning surface? Basically burning surface area is what we are interested. Initial should be easy. So finding a burning surface area is very important for solving this kind of problem. I would urge you guys to understand it better. If you have any questions, you can ask me. So then you
Sir, mass flow rate divided by burning rate into density of propellant.
okay, that is one way. Mass flow rate. So burning surface area, let's call it surface area SB. Okay. So mass flow rate divided by rho of propellant into burning rate. But this introduces lot of complications, right? You don't know mass flow rate. You only know density of propellant. You know the burning rate of the propellant, but burning rate of the propellant depends upon the pressure, so you don't know the pressure also.
So is it just 2 kRh?
Yeah, exactly. So basically, what do you see here is you have the grain here. Okay, this is the grain. Okay, and it is radially burning. So initially the burning surface is going to be the initial surface area of the grain, basically this round, right? This is going to be the initial surface area of the burning. So based on this you can actually find the initial burning surface area. And what would be the final burning surface area? Since it's a solid rocket motor, it is going to end only after the complete consumption of propellant. So this is the final surface area is going to be your final diameter of the whole rocket. So just using this grain and the length, you can directly find the burning surface area. Okay. So while uh, this formula is right, but the only thing is we didn't find out these quantities yet. We are going to find out. Okay. So to find burning surface area, so first is we need to know initial. Let's not put numbering here. So initial is, let's say, SBI, which is going to be uh, 2 pi r into length, or you can do pi d into length of the grain. This is the surface area of the inner surface area of this hollow cylinder. So pi into di into l. This is going to be your initial, and the final is going to be, let's say, SB final, which is going to be pi df l. Okay. So how much should that be? 0.03 meter into length is 0.5 meter. This is going to be pi into 0.1 into 0.5. Okay. So how much is that coming out to be? So this is, I am getting something like 47 meters, 4712 meter square. Okay, and this is 0.1 into 0.5. Zero 0.157 meter square. So this is how you can easily find the burning surface area. For this it's simple, but I think you have to be little careful while you are solving your assignments. So so I will ask few questions. Why didn't we consider this surface? This is also exposed, right?
But ignition doesn't happen there. Ignition happens only like the liquid propellant which comes inside, which is injected, touches the wall of the, let's say, cylinder.
No, ignition can happen there as well, but yes, it's. But I think this site is inhibited.
So okay, yeah, there is a, as sir said, it can be inhibited because you know they can add a inhibitor here to arrest it. But ideally, one thing I wanted to make sure Sai understand is there is no liquid propellant entering. Okay, so igniter is going to ignite and solid is going to get combusted and become generate gases. Okay, so there is nothing enters here. There is nothing enters here. Only igniter will ignite, and that igniter can be anything. It can be a heat source. It can be itself a small rocket. It can be anything. Just we need to have, you should give enough energy for the whole propellant body to start igniting, basically. So this solid propellant is so simple in terms of construction. You can think it as like a the rocket you use it during Diwali, right? In Diwali you used to send rockets. For that you just ignite it in the thread, and then inside there is a solid propellant inside. Here we call it propellant, there it's just pyrolysis, pyrokinetic materials inside, so that is going to get combust and then it's going to show everything else. So here also the same thing happens. There is no liquid entering. Okay, there is no liquid entering. You just ignite it at this point, basically anywhere in the system, and then surface starts burning, and then it starts generating gases. But only thing is, we also told in the in the question itself, it's a radial burning solid propellant. So you can take this also as an idea that it is going to be only burning radially, and so we can ignore these surfaces. But the same thing you cannot do it in your assignments, so you should be a little careful. Okay, so you should find out what is really the so this surface can also be exposed to ignition. This surface can also burn. There is no reason for it to not burn. But since we said it's a radial burning, we are ignoring that surface. Okay, so once you ignite, the flame actually spreads everywhere in the surface. Flame actually spreads even in the side faces. So only if the inhibitor is there, you won't be able to see this. Okay, so let's go ahead and get the B. So the next question is about initial and final equilibrium pressure. Okay, so let's try to solve that. So how do we find initial and final equilibrium pressure? I think there is a delay from my iPad. Maybe I will disconnect and join again. So while I do that, can you guys tell me how do we find it? Oh yeah, I ended the meeting. Shit. Hello, I'm extremely sorry. Somehow this got disconnected. I hope everyone is able to join. All right. I'm sorry it got disconnected for everyone. And there was some problem from my iPad. I think now it is working properly. I think only Ram sir was not able to join. Okay, he also joined. All right, so I apologize for ending the meeting abruptly. There was some problem with my iPad. So, all right, I think we are quick. We are back. So, was someone saying anything? How do we calculate the equilibrium pressure?
Can we use the equation that they've given?
Equation they have given. Okay, what is that
So
equation?
from quick mass flow and mass flow, mass flow that we can make it. Mass
Could,
flow must cause it in the pressure.
True. Yeah.
So from there we can find out.
True. Yeah. So that is what we are going to do. You are right. So mass flow rate you can write it in terms of or it is coming from the C star definition, PCAT by m dot. Since C star is given, we can directly use this. Okay. So so we need to find pressure. So pressure is equal to m dot into C star by AT. But only thing is we need to find m dot. So as Tanisha said earlier, we can use that m dot formula, which is nothing but the rate at which the propellant burns. Okay. So it's going to be density of propellant into RV into SB. SB is nothing but the area of the burning surface at any instant. This is an instantaneous mass flow rate is what we are talking about. The burning rate at that instant and burning surface area at that instant is what we are talking. Okay. So if we put all these things together, then we get the formula which we are really used to use it to solve the problem. C star by 8. So now one question remains. So still the RB is a function of pressure, right? RB is equal to, maybe we can write this as AP power n, where A is equal to, it's also given 0.019 and n is equal to 0.38. Okay, area of throat we can find it, and C star is also given. SB we initially found out, so let's try to find the initial equilibrium pressure. So initial pressure is going to be rho propellant, RB initial, SB initial. C star is not going to vary because it's a performance parameter, divided by area of throat. Area of throat is also not going to vary. And SBI we already find out before. So only thing is we need to find RB at RB initial. How are we doing it? So this is PCI, or we can simply write PI, right? It can also simply write PI. So let's try to substitute everything here. Others are straightforward, but RB is what we need to give a little care because it also contains the pressure. So P at I power n. So you can take this to one side and then you can get the answers. So Pi by Pi power n is equal to rho propellant SPI C star by AT into A. So Pi is equal to Pi power 1 minus n, here it will be. So I think this formula is what Sai is referring to, I guess. Okay. So basically I am just deriving the same thing, nothing else. So this is nothing but the mass conservation equation. Can you guys guess what is this? How did we get this? Can you guys relate why I am telling it's a mass conservation equation? This is
So the rate at which the mass is burning is equal to the mass that is ejecting out from the nozzle.
right. Wonderful. Thank you, Tanisha. So basically, what we are telling is this m dot into c star. So this part is coming from the nozzle, and this part is coming from the propellant, and you are just equating these two, which means the mass burning rate is equal to the rate at which mass going out of the nozzle. So basically, it's kind of like a steady state analysis. Please remember that whatever the mass comes is going out, so it's in steady state region we are talking about. Okay, and that's why this is true throughout the steady state region. But this is not true during the ignition, like initial uh, you know just during the ignition it is not true, and also not true during the end of the burning. After the propellant has burned, there will be sometimes there will be some gases going out of the nozzle, which was already present in the chamber at that time. Also, this formula is not true. So this is true during the steady region, steady operation region.
So why are we saying it as equilibrium pressure?
So um, so basically here what we are telling is um, this steady is what we are actually telling it as an equilibrium. In fact, you are telling that mass flow rate entering and leaving is equal. So in that way, that is the sense they are calling this as an equilibrium pressure. If not, you will just call it as a chamber pressure, right? So basically that is the reason. And also the other thing is your the combustion is going to happen at the you will end up getting equilibrium temperature at this during this combustion region. But all these are ideal. In ideal cases, you will end up having equilibrium temperature and also the equilibrium pressure. So why we say equilibrium temperature is we saw that in the last classes, also in the lectures also we do equilibrium calculations, right? So we'll say heat in the reactants and the products are the enthalpy of reactants and products are same. If it is same, if there is no adiabatic heat loss, then the temperature it reaches is an equilibrium temperature. So similarly, equilibrium pressure also. And also we say that the products are in equilibrium, so that is where equilibrium temperature came. And in addition, we say mass flow rate is same, so we say equilibrium pressure.
But
Okay. So in fact, this actually you no need to write in terms of I. If you put I, it's going. If you put final also, it's going to be same. So let's try to quickly find the pressure. So rho of propellant, I hope it's 1400 into SBI 0.04712 into C star, which is also given. Okay, C star is 1400, this is 1700. 1400, this is 0.019 divided by 80, which is going to be pi by 4 into 12 mm, 0.012 square, whole power 1 by 1 minus 0.38.
Sir, I think we have to convert 0.019 also into meters because they're given R in terms of millimeters per second.
Oh, okay. All right. I'm sorry about that. R is in terms of millimeters per second, so you multiply it with 10 power minus 3. Okay. So
Yes, sir.
this will give you, correct? Hmm. So what is the initial pressure you are getting? Let me write down final also, which is also going to be 157. So if you guys found the answer, please let me know. This will be your final pressure. Let me quickly check my recordings. Okay, it's going good. So basically we just need to change the burning surface area to the final, so you will end up getting the final pressure. So did anyone find it out?
Is it 6269.1?
6 for which one? P initial
P initial.
6269.1.
3.
Are you sure it's in bar or pascals?
It should be Pascals, right? We've taken everything in standard units.
Okay.
I'm getting in megapascals.
How much is the
Then 7.857, 7.85 megapascals.
7.85 megapascals? So we have two different answers here.
Yeah, 7.857 megapascals for P initial.
7.857 megapascal looks very high to me. Okay, 7.857. Okay, if that is the case, it's fine. 7.857 megapascals. Okay, how about this one?
So these SB
54.745 megapascal.
54.745
745.
megapascal. So we can clearly see that the pressure is, as Ram sir was telling, we can see that pressure is keep on increasing. It should increase. Can you guys guess why the pressure will increase for a cylindrical crane?
SB is increasing.
So why? So basically, since it's radially moving out, initially the surface area would be small, and as it moves out, surface area will be large. So large number of gases enters the chamber, and if large amount of gases enters the chamber, pressure inside the chamber is going to increase. That is what we see mathematically also. All right. That is done. The next is to find burning rate. Similarly, initial and final burning rate. Let's try to find. So for that we already have the relation, which is APN, but only thing we are going to use is we are going to use initial and final. That's it. 0.019 into 7.857 into 10 power 6. So you need to be little careful here, because you should see whether the pressure is given in pascals or megapascals. So this is given in pascals, so no need to worry. And then you will also find the final burning rate, basically 0.19 into 54.745 into 10 power 6 whole power 0.38. So how much is this coming out to be?
Is it 7.92 millimeters per second?
Wonderful.
Yes.
So is this coming out to be something like 16.57? So I'm getting something like 16.57. Please check.
Yeah, yes, 16.5.
Yes.
Thank you. So okay, so far so good. We have completed this. Now we need to find the burn duration. I think initial and final mass flow rates would be even straightforward, and also thrust would be straightforward. Only thing is this burning duration we need to find out. What is the total burning duration?
Burning rate is radial length divided by burning duration. Radial length is RBF, no, like final radius minus initial radius.
So, but burning rate is not constant, it is a function of pressure, right? So that is, so you are telling that this is I am going from Ri to Rf with some Rb, right? So basically you are telling dRb by dt, if we just integrate to be, so this will be some value, and you are just asking me to integrate from Ri to Rf. But this is not a constant value, it's a function of pressure, which is also a function of time. But the spirit is right, basically. But only thing is we need to be little careful while doing this. So you cannot take burning rate to be constant, because burning rate is also increasing from 7.92 to 16.57 meters per second.
For quick calculations, can we take the mean burning rate? Use that?
We could do that, but the problem is it may not be accurate.
It's a quick
So
calculation.
what we can do actually. So but what we will do is we'll rigorously also find, and after that we will follow your suggestion also. We'll try to find out the use the mean burning rate to find out, and then we'll see how different is this. It is easy to find out using mean burning rate. You are right. So basically what we can do is, to begin with, you can use the RB. RB is nothing but burning rate, which is nothing but dr by dt, the rate at which radius is regressing. Okay, so this I think you need to be, so for this again, this is a hollow cylinder, it might be easier, but you should be little careful while doing it for the other geometrical section. Okay, so that's why I'm going a little slow here. We can even simply use the the formulas which professor derived, but I wanted to uh, specify here a little bit, take some time here a little bit. Okay, so this is our burning propellant, and this is the center line, and this is our radial coordinate. Okay, it says radial coordinate. Now what I'm trying to do is, you need to, so you can let's say this is the burning surface, then this is your Ri and this is Rf. So now, since the pressure and radius is going to be regressing at a different rates, you need to actually integrate it, including all these effects together. So that is what we are going to do here. So basically we know that Rb is equal to a p power n, and what we also know is we can use the pressure. How pressure is going to vary, that is going to depend on the burning surface area. So that is also we derived a little while back, this one. So we can use this relation also, which is rho propellant SB, which is a burning surface area, C star A by AT whole power 1 by 1 minus n. Okay, but only thing during which these things vary, what are the things during the propellant regression is going to vary? The pressure is going to vary with respect to time, right? And the burning surface area is going to vary with respect to time, and but rho propellant area, these things are not going to vary with respect to time. Similarly, C star A is a parameter, pre-exponential factor in RB, right? So and n is also not going to vary. Only thing is pressure will vary, SB will vary. So let's try to separate these two things little bit. So maybe we can write this as so rho propellant SB, we can write it as pi d into L. And what is this d? That d you should be little careful. Let's say this is your, at any instant of time, this is your radius r. Let me write it capital R. Okay, and the corresponding diameter is what capital D is. Okay, into C star into A divided by AT whole power 1 by 1 minus n. So now pi and L is also not going to change, so we will club all these things together. Rho propellant pi L C star A by AT power 1 by 1 minus n into D power 1 by 1 minus n. This is the pressure, where this part is not going to vary. This part is not going to vary, it's just a constant, but this part varies. And what we will do is, we will try to substitute it here. Okay, if you do that, RB is equal to A into P p power n. So this becomes A into rho propellant pi L C star A divided by AT whole power 1 by 1 minus n d power 1 by 1 minus n power n. Okay, so this you can rewrite this as, you can add these two together, and maybe you can write, maybe we can take this as, let's say, some factor. Which one we'll take something like b. We are using a everywhere, let's take it b. So you can use this as a into b power n by 1 minus n into d power 1 by 1 minus n. Okay, and this is going to be equal to dr by dt. So now you have wrote this dr by dt equation in terms of diameter, which again you can change and write. Maybe we can change this side and write this as r is nothing but d by 2. So you can write this as dd
So
by
the
dt.
powers are n by 1 minus n.
Sorry, into b power n by 1 minus n into d power 1 by 1 minus n. This is okay, this is also should be n by n minus 1.
Yeah.
Okay, thank you. So now you can write this as dd is equal to dd by dt is equal to 2abn by 1 minus n into d power n by 1 minus n. Now you can easily integrate because this whole thing is a constant. Okay, so this you take to this side, and this you rewrite this as into dt. This you can integrate. So this can be integrated from initial diameter to the final diameter, and the time can be 0 to total burning time, TV. Okay, now from here it should be straightforward for you guys to integrate and get the results. So similarly you should be so the only problem I believe you would face is to write this term SB. So this SB I am writing it as pi d into L. What if this also is available for burning? So accordingly you need to add an additional term. Okay, that term you should add and then you should calculate. So the same goes to I think one of your assignment was having a two cylinder. So there's one cylinder and there is another cylinder. So one is regressing inside, the other one is regressing radially outside. Okay, so at that time you need to take both of them into account while writing this to this. Okay, then only you will be able to get.
Now,
Okay.
you see, if you include side base also, burning is occurring, L will be reducing. So from the side also burning is taking place, progress lengthwise. As a result, length will continue reducing.
Right. Yeah.
How do we take it?
Okay. So so it's a you can think about this a little bit. It's the same logic. So from here this will be your initial, let's say. After some time, here also there is a burning rate, so it will regress like this. This also will regress like this. So you will have something like this. Right. So this will be like this will be at time t equal to 0. This is at time t equal to 1 T1, let's say. Okay, now the burning surface area, you can write this as pi into, let's say, let me draw a coordinate, then only it will be easy to understand. So this is the surface, this is R. Okay, so burning surface area is going to be pi into D, or let's write it in terms of pi 2 pi R into L, where this L is going to keep on changing. Okay, so we also don't know that. So this is the L we are talking about, but this L also will keep on changing. Okay, 2 pi R into L plus, what is the total surface area? This surface area also plus, so this surface area is what I am writing as a 2 pi RL, and this surface area is going to be how much is going to be R naught. Let's write this as R naught. So R naught minus R. Right? Is this clear till now? The burning surface area? 2 times. But only thing is, I'm telling that L is also variable. We'll come to that, how to find the L as a variable. So only thing is, this is the length and the radius is R naught minus R, this length. Okay, and also it is so it is a circular, so it's not just R naught minus R, so it should
Yes, it will be pi r square thing.
Pi into R naught square minus R square.
Bracket. Okay.
So pi into R naught square, then there won't be 2. So pi into R naught square is the whole area minus pi into R square. So now R is also variable, L is also variable. Now you need to express L as a function of, now what is RB? RB is going to, for the length, so RB can be used for the length also. So what I am trying to say is, this surface area is going to regress with the rate of RB. Okay, so you can write RB is equal to dr by dt, and also you can write dl by dt. Okay, so the length is keep on reducing, so it can also be written as minus of RB. Till now, is it clear?
Yes.
So the rate at which this is regressing is going to be negative of RB, because length is keep on reducing. Now we need to use these relations together to get this burn time. Okay, so it's not a one relation, it is actually 2 relations. Okay, so let me quickly check in the book whether whatever I wrote is right or wrong. Different grain configurations. Okay, in the books they didn't give. All right. Yeah, that's fine. So, but this is how you will do it. Now the question is, how would you arrive at the burning time relation, right? So mm, I think you may need to solve it together. Cannot be, we cannot write it down separately for this, but you can solve these equations together to get the results. So what is the other equation you will solve with this? So the other equation would be rb equal to a into pn, and we know the pressure is equal to rho propellant SB C star A by AT whole power 1 by 1 minus n. So basically you will solve this two with these two, I mean including these two together. So it's like now it become like a system of equations. You have two variables r and l, so you need to solve it together. That is how I see here. So is that clear what I'm trying to say?
Yes.
Okay, so I hope I didn't confuse you too much. So basically, for just for the sake of completion, I am writing this here. So when I say I solve it, you can solve it using numerical methods. Okay, since it's a dr by dt and dl by dt is equal to minus of rb, and sb is equal to 2 pi rl plus pi into r naught square minus r square. So the reason is the L is present in L and R are present in both this relation. L and R are present in both this relation. So you need to, this is a coupled system of equation, you need to solve it together to get the results. Or you can go through advanced mathematics to get this. Yeah. Alright. Anyway, so at this point we are not considering that, so we no need to worry. Yeah, only when you have two variables this would be a problem, otherwise it shouldn't be a problem. Okay, so what happens if we do this integration? All these things are not going to depend on time also, so you can take this out and you can simply write this as 2ab n by 1 minus n into tp. Okay, and this part you may need to write it as d power minus n by 1 minus n plus 1 divided by minus n by 1 minus n plus 1 varies from di to df is equal to 2ab n by 1 minus n tb. So we are interested in tb, burning time, is equal to 1 divided by 2ab n by 1 minus n into, so how do you write this? df power 1 minus n by 1 minus n minus di power 1 minus n by 1 minus n whole divided by 1 by n by 1 minus n. That's it. So you just substitute all the values here, you will end up getting the answer. So 2 into 0.019 into 10 power minus 3 because these are in this is in mm per second, and B we need to find out. We'll find out. Into df is 0. How much was df? D final, okay, D final and D outer both are same, so 0.1 power 1 minus 0.38 by 1 minus 0.38 minus di, which is 0.03 power 1 minus 0.38 by 1 minus 0.38 whole divided by 1 minus 0.38 by 1 minus 0.38. Let's try to find B first. What did we say B to be? Rho propellant into pi, this whole thing. So this is going to be 1700 into pi into length of the grain is 0.5 meters into 1400 into 0.019 into 10 power minus 3 divided by pi by 4 into 0.012 square. So you find the B, substitute here, and you can find the burning time. So if you guys completed, let me know. Let me also try to find out pi 0.5 1400 into 10 power minus 3 divided by pi into 4 0.012 square. So this B is coming out to be something like 628,055.55. If I put that here, do you have the final answer?
Not BB.
I'm sorry, I couldn't hear you properly.
No, I have only calculated B.
B, okay. So,
what written is correct.
okay, thank you. So TB is something like 1 divided by 0.35955 into 0.38 divided by 1 minus 0.38 1 minus, so it's 0.38.
So my answer is coming 0.74.
0.74 seconds. Is that Tanisha?
So let me check once. Maybe it is wrong.
Sure. So this is coming out to be 0.387 minus 0.03 0.387 divided by 0.387. So I'm getting something like 2.9 seconds. Let me know. Maybe you may need to be little careful while substituting A should be not just 0.019, it should be 0.09 into 10 power minus 3. same as the formula we got in the book. Let's see.
Yeah, 0.9 seconds.
Okay, thank you. I'm just cross checking once whether the formula whatever I wrote is fine or not. So they wrote it in terms of 1 minus 2n. Okay. 1 minus 2n by 1 minus n, 1 minus 2n by 1 minus n, 1 minus 2n by 1 minus n. So we get the same thing. Okay. Yeah. So only problem is if n is equal to see here it's easier. So n is 0.38, so there's no problem. If it's n is 0.5, then it's a problem. Then this is not applicable for n equal to 0.5. So which means like you need to go back a little bit. You need to substitute n equal to 0.5 over here in this thing before doing the integration. So now let's try the other way. So let's try to make RB mean and then let's try to find out the burning time. So RB mean is equal to, we can write it as RBI plus RBF by 2. So RBI plus RBF by 2 will be 7.92 plus 16.57. 7.92 plus 16.97 divided by 2, which is coming out to be something like 12.445 millimeters per second. Now the radius varies from so the outer diameter is like 100 mm and the inner diameter is like 30 mm, which means the outer radius is like 50 mm and the inner radius is like 15 mm. So the total delta R it needs to travel is like 35 mm. So then if I want to find the burning time, this is like some mean burning time, it is going to be delta R by this RB mean. Okay, so if we do that, 35 divided by answer, we are getting something like 2.81 seconds. This also validates that it's almost so you are getting a better estimate. It might be simple for this cylindrical grain propellant. You are getting 2.8 and the real result is like 2.9 seconds. So basically how much percentage difference you are getting? 2.9 minus 2.81 divided by 2.9. It's like 3% difference. This is what you are getting. So it's like something like 3% off. So if it is 2 seconds and 3 seconds is fine, but when it is running for a minute or so, if you are short by, let's say, if it is going for 100 seconds and if you are short by 3 seconds, then if you over predict it, it can become a problem. So that's why it's better to have a more accurate prediction in terms of at least that is true in rocket propulsion at least. But yeah, it's a good idea. We can get you can get an estimate of how much it will be. Alright, I hope everyone is able to get this 2.9 seconds.
Yes, sir.
Okay, thank you. So then I think this one is also done. Now it's straightforward. Now you can easily find out initial and final mass flow rate and initial and final thrust you need to find out. So that should not take much time. So let's try to find out mass flow rates. So this mass flow rate, you can either use the nozzle mass flow rate, m dot is equal to PCAT by C star, because we know PC and C star and AT is not varying. PC at initial and final also we know. Or you can use the propellant burning rate, which is RB at I and SB at I also we know. So we both already calculated. Both of them we already calculated. So either way you can use. So m dot initial is going to be either PI AT by C star, or it's also equivalent to writing propellant RBI SBI. So both will give you the mass flow rate, same mass flow rate, and then the final is going to be simply this rho propellant RBF SBF. So either of the formula you can use it to find the mass flow rate. So can anyone quickly tell me what is the mass flow rate you are getting? So let me also try to calculate. So C star we know it's 1400, and the area of throat we know pi by 4 into 0.012 square divided by 1400, 8.078 into PI is initial PI 7.857 into 7.857. So this is coming out to be some 0.635 kgs per second. Okay, 7.857.
0.63%.
And then final pressure is 54.745. 745. That is some 4.422 kgs per second. This is the mass flow rate I am getting. Then finally the thrust. How do we find the thrust?
Chamber pressure into throat area into CF.
Chamber
Specific.
pressure, throat area, CF.
It will be PC, it will be PI and PF respectively for the cases.
Why is that? How is this the thrust?
Sir, it should be m dot into CF into C star.
Right. So basically we are trying to get it from ISP. Okay, so ISP is nothing
Okay.
okay, ISP is C star CF. So this is for thrust at the exit of the nozzle, right? So that we know from ISP, it's ISP by m dot, or sorry, ISP into m dot. So we can write this as C star CF into m dot. So C star CF is same, so you make it initial and then you make it final. That's it. CF is 1.1, so it's nothing but 1400 1.1 0.635 1400 1.1 4.422. So I'm getting something like 978 newtons, and this one I'm getting like 6810 newtons around that. So let's say if I want to plot this, how will it look? So let's say I am plotting pressure with respect to time. Okay, so ideally how it should look is, let me plot that also. Ideally it should look something like this. It will be something like this, and then it will drop and become something like this. But we won't be able to capture everything here. Only things we will capture here is this straight line. Since it's a steady state approach, this is the only thing we will be able to capture. So it will be something like this. So ideally what we did was, this is the dB we were trying to find out. So this is without considering the initial transients, as I said. Okay, so this is the pressure. So everything like thrust, mass flow rate, everything is going to vary like this. The reason you have this kind of this thing is due to that exponential factor, n by 1 minus n. So r basically 1 by 1 minus n. So this is what is giving you this kind of behavior. Okay, so does anyone have any questions regarding this? I think we are done. I think this question is pretty straightforward. Only thing is you need to be little careful while finding the burning surface area, and also using the burning rate to find the burn duration. Otherwise it's a pretty straightforward usage of equations. All right, does anyone have any questions?
Yeah, I have a question. Can you access the solution by the reverse of assignment 6?
Assignment 6, okay. Let me try to open that here. Week 6 assignment. So which question?
Number 19.
Number 19, okay. Temperature of the combustion products of the
Look at the solution.
okay. Solution. Twelve, 13, 19. Okay. So is the solution wrong or something?
Yeah. You
Okay.
see, at
Mm-hmm.
here, we've written when we have combustion products, you know,
Mm-hmm.
and then the ground emission, there is a relation. It's H2.
Mm-hmm. So this 373 minus 298.
Yeah, this should be 75. You put in 100.
Mm, could you please come again? This should be.
You see, in the solution next line,
Mm-hmm.
we have written NH2O multiplied by CPLH2O
Right.
be multiplied by 370 minus 290.
Correct.
Now CPLH2O is 90. So 2 multiplied 90 by 100 unit. Should be
Okay.
75.
Okay. So was there a mistake in calculation? Is it?
No.
So 2 multiply by 90 into 100. It's here, right?
Uh,
1 second.
why should be 100?
Okay. So 373 minus 298 is not 100.
Yeah.
Okay. 75. It should be 75 then.
So if you use 75, the TF will come out less than 2757. But small.
So how much is it coming out to be? 4000?
I calculated it was coming out to be 3596.
3596. Okay.
If that is so, then the question 20, because the same PC has to be used.
Question 20. Okay.
Next. So TC, instead of using 4757,
Mm-hmm.
just 596.
Okay.
So
Okay.
that will change the value of C star also.
I see. But but what I feel is 25 Kelvin difference in CP of H2O is creating like 700 Kelvin difference in adiabatic flame temperature.
Yeah.
Okay, that is too much actually.
That can do that calculation right away here.
Yeah, sure. Let me give it a try. So delta HC is right, 883 kilojoules per kilomole.
That is right. That's right.
Okay, so let me try from here. Is anyone from the audience have the similar problems?
Yeah, I wasn't able to solve this question.
Okay.
Sir, my temperature is coming 3800.
Okay, so similar to Ram's temperature. Okay.
My 900 something.
Okay.
Observe. But if you have to look at this,
So this delta HC is going to be so N of CO2 and CPs are CO2 is 1, is it? So is there, okay, CO2 is 1, 2 H2O.
it has to be solution as you have to do the calculation that 63 EF minus 98.
Okay, so 1 second. So and then you have latent heat of vaporization, and then we have CPG. So let me give it a try. So we have one second, I actually couldn't why do we add latent heat of vaporization in the temperature? Because we have reactants and then you have products. Okay, that's all right. I think this is the flame temperature minus 298 Kelvin. So this is like temperature required to heat up the products.
Yes.
Okay. And then H2O is like 2 times Cp of H2O, but it's a liquid. It is from 3 till 373 minus 298. That is also right. And then you have 2 times latent heat of H2O, and then you have 2 times Cp of H2O, but in terms of gas, into Tf minus 373. Alright. This is the total energy required to heat up. Okay, now Cp of CO2 is provided. Cp of CO2 is 63. So all these are in terms of moles, so we can go ahead. So 63 into 63 plus 2 times Cp of H2O, which is 58. Sorry, 58, right? 2 times 58 into Tf minus 298 plus, this is 75, 2 into 75, 150, 150 into Cp of H2O is liquid, 150 into 90, so 13500 plus latent heat of vaporization of liquid is also given. 19 is, was it given here, latent heat of vaporization?
Yes. No.
Where was it given in the question?
Oh, maybe I'm taking another question.
Okay, what did they did in here? Here they took out it to be 40 into 10 power 3. It should be somewhere given here only.
It's given another question.
So it's given in the vaporization is 40 kilojoules. So 40 into 10 power 3 kilojoules. This is 883 into 10 power. What have they given? Is it kilojoules per kilomole or
Good.
kilojoules per mole? So I wrote it wrong. Kilojoules per mole. So if it is the case, let's try to find out. 2 into 40 10 power 3 plus 13500, 883 into 10 power 3 minus answer divided by 63 plus 2 into 58. So I am getting Tf minus 298 to be equal to 4410.6. So Tf is coming out to be plus 298, 4708.6 Kelvin. So did I make any mistakes?
No, mistake only apparent is 175.
But still I am not, I am getting 4700 only. So Were you also getting 4700 or 3900 feet?
Then I can take my calculation. Only yeah, I only saw the sort of
Okay,
some
okay.
recommended is mentioned, so I thought
Mm-hmm. So probably you can check once. So basically, what I feel is having a 25 Kelvin difference in the heating of products should not lead to 700 Kelvin difference in the adiabatic flame temperature. So in that way, also we can think about it. So this also makes sense. So 25 Kelvin difference actually leading to since it's a 2 mole leading to like a 50 Kelvin difference, approximately speaking. So my
you're
product.
not the same. Not the same. So
Could you repeat? I couldn't get you.
but you're getting 4757 here.
Actually, I'm getting 4708 Kelvin. But yeah, I think there is a mistake. They added this 100 Kelvin. That could be the reason why they have a little higher temperature. But probably it should be 4708 Kelvin. And if that is the case, C star should be around.
But I will also check once again.
Haha, sure. If that is the case, C star should be around 8314.5, 4708.6 divided by molecular weight. .7 square root.
Put 75 there.
Mm-hmm. So C star I'm getting something like 1890 meters per second.
So 596 minus 6 and maybe I am not wrong.
So so you were still able to get only 4700 Kelvin or 3900 Kelvin?
I've not done calculations. That
Okay, sure. Please do it and let me know. So probably I think yeah, they might have miscalculated a little bit, but still the I think temperature lies in the range of accepted answers. So maybe they can move the range, relax the range a little bit, maybe. Yeah. So this is coming around 1890. So 1820 might be same, but 19 they could relax the range a little bit. Otherwise everything is
yeah,
okay.
restaurants are okay.
Okay.
These two, they are linked to each other. Maybe I've done wrong calculations.
Mm-hmm.
So I
One
have
sec.
a doubt with the answer of question 3 as well.
So once again, before I go there, I think I made a mistake here also.
Okay.
Okay, 1 second. I think I made a mistake here.
But can you recheck the calculations?
Yeah. I'm checking. I made a mistake here. I'm sorry. So this should be. This is still 63. This should be 2 into 58 into TF minus 373. So I took a shortcut over it. So this is 789500 is equal to 63 into TF minus 298 plus 2 into 58, which is 116 into TF minus 373. So 7895 63 into 298 plus 116 into 373, 7897 789500 plus this divided by 63 plus 116. Okay, so I am getting TF to be 4757.2 kilo.
Oh, 757. Only thing, are my calculations are wrong.
Probably I think whatever they gave here, they wrote it as 100, but I feel it's a 75 only. The final answer is right. Yeah.
Why not? I also get it saying 4757. By how I can.
Okay. Then I think C star also would be same. Yeah.
Huh.
Right. Okay. All right. Thank you. What was the other question? Was it Sai? You wanted to ask a question?
So I
Okay,
was
Akhilesh.
asking.
Yeah. Please, Akhilesh.
So it was question 3, the MCQ one.
Okay.
The highest adiabatic flame temperature.
Mm-hmm.
They have given stoichiometric, but so even in the lectures, the professor rigorously proved that fuel-rich part gives us better temperature. That's why exactly why the fuel-rich mixtures are used in combustion, so that we get the highest possible temperature of combustion.
So basically, what happens is,
That, mm,
so basically it actually depends upon the system you use. Sometimes even oxidizer rich will give you the highest adiabatic flame temperature, but here the question is about the it's simply adiabatic flame temperature is highest in which combustion. So it depends upon the lot of aspects. So in this case, I think in an ideal scenario, it's always stoichiometry is going to have higher adiabatic flame temperature, but
mhm.
in real cases, it can either be fuel rich or it can be fuel oxidizer rich. But when we say fuel rich and oxidizer rich, it's not that much fuel rich and oxidizer. We are talking about like equivalence ratio of 0.01, 1.01 or 0.99. So there it might so okay, let me try to draw a graph and show it to you. So let's say this is the equivalence ratio of 1, this is let's say 0.5, this is the temperature, let's say. So this is like 0.98 and this is like 1.02. So there is a possibility that it might be little high in the off stoichiometric conditions, but all these things are going to be more near to the stoichiometric condition. Okay, it might be off by 0.98 or 1.02. That happens in the real case, but getting a real case adiabatic flame temperature is not easy. Okay, you have to run a separate thermodynamic calculations, chemical equilibrium calculations to get the adiabatic flame temperature. So in our course, we are not actually dealing with that. We are actually assuming stoichiometric products, or assuming some certain number of products, and we are trying to manually calculate it. When you do this calculation, it always lies in the stoichiometric condition, the adiabatic flame temperature. The reason to go it off stoichiometric is due to the high temperatures and dissociation of products, CP of the product gases. All these things might shift your highest a little bit, but it will always almost remains in the stoichiometric condition. So it is true that professor was giving you some idea about it is not all, it's not always in real scenarios it will not happen, but our from the scope of this, I think assignment, I think that is what they are trying to say. Maybe you can raise this question in the forum. Let's see what professor replies. Okay. But you understood the concept, right? So it's always going to be stoichiometric, but it can be little bit off. That is always seen. Little bit off.
And he actually explained it by gamma. The value of gamma was changing with the fuel rich when we go to fuel rich. So
But that
the
is
change in value of gamma eventually changed the value of CP, and therefore it lowered.
so. But that is basic. It actually highly dependent upon the fuels you are actually dealing with. There are few fuel rich also. There are few fuel lean also. In of stoichiometric conditions, you can see this effects. So yeah, but please do raise this question in forum. Let's see what professor replies. Okay.
Sure, sir.
Okay. Any other questions you guys have?
I have now.
Sir, I actually had the same question I asked in the beginning of the class about the divergence angle.
Mm-hmm.
Hello?
Yeah.
Yeah, so in the class he actually explained whatever you said semi-divergence angle. In the class he actually told that is the divergence angle.
I see.
So from 0 to like alpha it is, we take divergence angle, and somewhere in between we take alpha by 2, like it is the mean value.
Okay.
So because he told that I went according to that and I got like 7 to 8 questions wrong because of that in the assignment.
See, but so as far as I follow, he only wrote this book actually. There is this rocket propulsion book by Professor K. Ramanmurthy. Yeah. So this book also actually tells that the upper half is actually semi-divergence angle. So probably some, I'm not sure which.
How he explained in the class was like in the lecture.
But there should
it
be a different occasions. He must have been asked a little differently, right?
No,
I mean,
he
it must
actually
have
did not take beta. He used alpha,
Mm-hmm.
the letter, but yeah, he just used it as alpha as the divergence angle, and he told what divergence angle is from the half of the nozzle. So the whole thing would be like 2 alpha.
That is fine. Why would that be a problem? If the divergence angle is alpha, if the semi-divergence angle is alpha, the divergence angle will be 2 alpha.
Yeah, but no, actually in the class he told divergence angle is alpha.
Okay, then
So
semi-divergence
the whole
angle
will be alpha by 2, which comes somewhere in between 0 degree line and the alpha, like to one of the sets.
So I think you are confused. So semi-divergence angle is half of the divergence angle. So if the formula you wrote it for semi-divergence angle, and whatever given is divergence angle, then you need to divide by 2 and substitute it. So you should be little careful with the formulas. Was the formula written for semi-divergence angle or a divergence angle?
He wrote it for both of them actually. He wrote 1 plus cos alpha by 2, which is where he told that is like the divergence angle.
Yeah.
Then he told he marked alpha by 2. Like let's say if it's like 45 degrees, which is the half angle, alpha by 2 will come somewhere between 22.5 degrees.
Correct.
From the horizontal line. So he told alpha by 2 is that line.
Okay. So actually what you have to do is you derive that formula. Okay. This is my suggestion. You derive the formula based on whatever he said, and based on that you calculate it. That will come out to be proper, I guess. Okay. So
Okay, yeah.
once do that exercise.
Sir, is the derivation there in the book? Because he did not really derive it in the
It's
class. He just took it as alpha by 2.
so no, alpha and alpha by 2 is similar. That is the definition we follow. Only thing is, what I'm trying to say is, you are trying to find the losses, right? Divergence losses.
Yeah, the divergence.
So divergence loss is it's going to be mass flow rate times the velocity, right? The mass flow rate also will be cos alpha by 2, and velocity also will have a so it's a divergence loss. So what is really the force you are getting along the actual direction you calculated, and then the total force you subtracted, that will be your divergence loss. So when you do that derivation by yourself, you will end up having either 1 plus cos alpha by 2
Cos square
or
alpha.
1 exactly. So that either you will have cos square alpha or you will have cos square alpha by 2 based on the definition he mentioned in the class. So do that
Yes, sir.
do that once and see what you
I
get.
have a question.
Mhm.
This actually pertains to assignment. My question I think is, I have made an equation. The question of C12H26 with oxygen.
Okay.
So
Which
I
question?
have the product item that I have written is assignment 7, question 16 onwards.
Okay.
Now, the product items I have written,
Mm-hmm.
it should be a fuel rich mixture, and there I have included carbon also in that.
Okay.
I am not getting the CP value of carbon given data.
I see. Okay. CP of
So
carbon is not given.
I picked up from the internet
Mm-hmm.
carbon specific for carbon, actually two different websites and giving different values. So
Okay.
I thought must be around only 1.5 per mole or something like that.
Okay.
Kilojoule. So I had used that
Mm-hmm.
and tried to find out yeah. But it's molecular mass of pellet decimal basis, and lastly I have to find out the value of temperature of the plastic particles.
Hmm.
So, is it possible to have the carbon as a product item if the fuel which we set that right? Am I on the right lines?
So yeah, actually for these calculations you can have carbon in the carbon atom as a separate product.
Carbon specific, it is not given in the data.
Yeah, then I think we should think a little bit. Probably you may need to revisit the products you calculated again, because carbon is being first oxidized with CO. So probably all the carbon might get oxidized by CO based on the mixture ratio.
I should
So
not
how
have-
many oxygen atoms you are getting it for the
I
mixture
have-
ratio of 3.2?
No, signature requirement is justified. I am getting 17 moles of oxygen.
Okay, 17 oxygen atoms,
Moles,
molecules. Okay.
1 mole of C12H26 and 17 of oxygen.
Okay, O2. Then we have enough to oxidize to CO, right? So we have only 12 carbon, and we have 17 oxygen atoms, which is like 17 into 2, 34 oxygen atoms. So 12 can be used for CO, and the remaining we use it to form CO2.
First preference is CO or CO2?
First preference is CO. That's what is being given. The fuel is first oxidized to CO, thereafter to CO2. So I don't think so you will be left with any carbon. Instead you will be left with CO probably.
So what I am trying to do, I will first try to form CO2
Okay, okay.
Later CO.
First it should be CO. First should be CO.
That is whatever oxygen is left over after water formation.
Hmm.
CO should be next finalized, and after that, whatever is left over,
Hmm.
CO.
Correct. So since it's a 26H2, probably 13 atoms will be used. So 34 minus 13, 21.
H2O.
So you still have 21 oxygen atoms, looks like.
Yes.
And so we can first form the 12. So if 12 is gone, we still be left with 9 oxygen atoms. So then
Okay.
maybe remaining oxygen atoms you can use it to oxidize CO to CO2. So
Uh,
probably you will not have carbon left based on your calculation of mixture ratio for 3.2.
See, 12, we have already used 12C, and 9 is remaining. So,
So the remaining, so we have 12 CO, 9 oxygen remaining. So we can, in that 12 CO, we can, oxidize 9 CO to CO2, like that. So that's a stepwise process.
so I should not use all 12 Cs.
Hmm.
Cs for
Right,
CO.
first, correct,
I will try.
correct. Okay.
I realize I have calculated wrongly the assignment 6.
Okay.
That I placed. My calculations are wrong.
Okay.
That
No
is not
problem.
set.
It's fine. No problem.
Sir, if I have a technical complaint, where should I give the complaint?
You can mail it to NPTEL. You can also. So, is there a way to put it here? Yeah, I think you can mail to NPTEL. That shouldn't be a problem.
Because last time I had changed a few answers and submitted it, the answer did not get updated.
Okay. There should be a feedback or something over here.
Actually typed it in the weekly feedback we get to Google Form.
Acha. No, I mean you don't need to fill the weekly feedback for this at least. You can give feedback, but this I think you should quickly contact NPTEL and resolve this issue because it's going to affect your performance, right? It's going to affect your result. So try contacting NPTEL quickly and see whether you can update it. Okay.
Yeah, yes, sir.
Give maybe there might be uh, some phone number also. You can give it a call.
Okay, got it.
Okay. All right. So I will update this. So if there are no more questions, we can meet next week. Thank you, sir. Thank you, Akhilesh. Thank you, Sai.
Thank you very much. Thank you.
Thank you, Krishna.